So we're actually broadcasting now. So again, on the test, these 3 questions, I had more than half the class didn't do this part to solve for X or didn't do it correctly. So, and if you want to know if you're one of them or not, I can kind of tell you at the end. But I want to give you guys a chance, because that was kind of a big chunk of points if you didn't do it, to do these again, either if you did them didn't do them at all or did them incorrectly. So obviously I'm not going to do the same exact problems, but I'm going to do one just kind of like this, just because we had more than half the class that kind of had a question on that. So, all right, so I will do one like B, but not exactly B. So instead of this, I'm going to do 10y plus, well, we'll go ahead and do minus. How's that? Minus 4xy equals, it doesn't even matter. Let's do 9, something like that. Okay, so if I want to solve for y, that means I need to get y by itself. So when I say solve for y up here, that means we want to have y equals something. Okay, and so we need to get y by itself. The tricky part is that there is a y in here and a y in here. So I can't just send everything in my second term over to the other side of the equation, because I still have a y, in that side of the in that term of the equation, right? So what I need to do is I need to get y by itself. So how I can do this is I can use my favorite property. For those of you who are new, that you don't know what my favorite property is yet, but my favorite property is the distributive property, but we're not distributing, we're kind of using the reverse of the distributive property. So what I notice in both of these terms, they share a y, okay? So I can actually pull out a y from both of these guys, and my y I'm going to pull out is over here. Okay, well, I guess we'll kind of scratch that off. I'm going to pull out a y. So if I pull a y out front, okay, then what's left is something that's in parentheses. Okay, if I pull a y out of 10y, I'm left over with 10. Okay, if I pull a y out of 4x times y, I'm left over with 4x. Okay, so what happens now is I have a y that's all by itself that's multiplied by the stuff that's in the parentheses. Okay, are you guys okay that this green form of the equation is the same as this original form of the equation? Does that make sense that they're the same? I'm going to kind of adjust my window here so I can see the chat at the same time. Okay. So Otto says, yes, that makes sense. Everybody's, that makes sense? Like if I then go and distribute this, right, distributive property, I'm back to 10y minus 4xy. All right? If I go and distribute it, that's what I end up back to my original equation. I'm going to erase that just so we, I think I accidentally, there we go. Okay, so now that I have this format, okay, now what I have is I have y times the stuff in the parentheses. Okay, so if this stuff in the parentheses was just a number like 3, like if this was 3y equals 9, you guys would be like, oh, easy peasy, I divide both sides by 3 and I'm done, right? But I have a little bit more than that that's being multiplied by y, but since it's the whole thing is getting multiplied, then I can actually divide this whole thing by what's in the parentheses. So if I can divide it by 10 minus 4x, okay, then I can also divide this side by 10 minus 4x. Okay, so then what happens is these cross off, and I'm left with y equals 9 minus, if I can get my 9 to right, 9 minus 10, 9 divided by 10 minus 4x, if I can say the right words. All right, so that's how I would actually solve for y. And then if I wanted to find what happens when x equals -5, then I could plug it into my equation and say, oh, well, that's 9/10 minus 4 times -5 and solve from there. Okay, so then you're just solving the problem. So I had like I said, more than half the class kind of missed either the solve for y or kind of didn't quite do it right. So I just thought, I'm going to let you guys have another chance at it. Does everybody understand now that they were able to see it? Does that make sense how you do these types of problems?
Yeah.
Cool. So if you would like for your chapter 1 test, consider it a test correction, you can retry A, B, and C I won't give you back the full points, but it'll give you a big chunk of the points back. And turn those in on Monday. Okay? That sound good?
Yeah, thank you.
Sure. Well, obviously, it's like if a lot of people miss a question, then something kind of was probably off by it. So either we didn't go over it enough or it was kind of hidden in there. So you guys try those out and let me know if you have any questions. Does anybody need to see a little bit more example with that, or you feel like you're good? All right, I'm not hearing anything, so I'm gonna assume you're good. Cool. All right, so now next up, I want to ask you guys if you have any questions on your homework that you've done so far. So we are up to I believe 2.6. Yeah, we're up to 2.6. I don't know where my PDF went, but we're up to 2.6, I think. So anybody have any questions on the homework up to this point that they wanted to go over? All right. All right, so then let's keep going with 2.6. Okay, so this is actually a cool, I think, a cool little section. It's something usually that's pretty new to students, so if you haven't seen it before, that's okay. So what this is talking about is 2.6 is actually talking about modeling data. Okay, so if we're talking about, you know, hours spent selling Girl Scout cookies and how many cookies that you sell, right? My favorite example. You might have a graph when you graph that data that looks something like this, kind of like a scattered kind of correlation. So what I mean by this is, let me pull this up a little bit bigger. Okay. So if you have maybe a coordinate plane, okay, and this is your y, and this is your x, right? Okay, and x represents the number of hours. This x is hours spent selling Girl Scout cookies, right? And this is amount sold. Okay. If you actually did this in real life and you tracked Girl Scout selling cookies and you plotted the data. So like say here, this is somebody sold for 1 hour and they sold, I don't know, 20 boxes of cookies, right? And here we have somebody that sold for 2 hours and they sold 40 boxes of cookies. But then you have somebody that sold for 2.5 hours and they only sold back down to 20. So when you are dealing with real data, like you're actually modeling real data, your data is probably going to look something like this. When you're dealing with like book data, you're going to get nice data that's easy to model, right? But when you're dealing with just information that you collect, say that you're in science class and you do a science experiment and you're asked to graph the data, it usually doesn't end up like perfect in some kind of a line or a correlation. It usually ends up looking something like this. And so then a lot of times what we do as mathematicians or as scientists is we try to model our data by the best fit. Who's heard that word before, like the best fit line or the best fit of the data? If you haven't, we're going to do that in Algebra 2. It's actually one of my favorite things to do. I think it's pretty cool. So what you try to do is you try to look at all the data. So this again is our hours spent selling Girl Scout cookies and the amount sold. And we try to make, this is called a line of best fit. So we try to fit the data to a line so that we can kind of say, oh, well, it looks like the more hours that you spend selling, the greater the amount sold. Right? Our data isn't perfect, but it kind of shows this correlation to that, right? And so this is what we would call a best fit line for our data. Okay, so that burgundy example is just an example of a best fit line. We can do that for all kinds of data. So this box shows 4 different types of data, right? This one, you try to fit the data and we draw a line this way that fits, right? Up here on the top left, obviously this data up here on the top left is like perfect, right? All of our data points exactly line up. This is probably an example of like something that you would see in a math book, right? All of your data looks really nice and perfect and matches up. Over here, we also see data that really matches up, right? But this is kind of sloped in a different direction. And then down here in the bottom, we see, oh, we're trying to match up our data. This is not as exact, but we're still able to make a correlation to our data. So I actually like this a lot. It's kind of cool to do. So one thing that you'll notice about this picture that I have here is that you'll notice underneath it has something called an R value or an R. Oops, and I don't have my papers right in front of me. Sorry. Let me grab my book out here real fast. So this R value actually has to do with how well does your line of best fit match up with your data, your actual data. Okay. And R, give me just a second here. R can go from -1 to 1. So the best R value you can get is -1 to 1. And it's called the correlation coefficient. Okay, so what do you notice about these two up at the top in the green? They match up perfectly, right? So the more perfect that your match, your line of best fit is, the higher your R value. So if you're a scientist and you want to model your data, right? You want to model whatever it might be. You want to model Girl Scout cookie sales. And you can make a model for your data that when you analyze it has a R value of either +1 or -1, then you've done a fantastic job of modeling your data because that means that your data works perfectly every single time. Okay? So think of R value. Again, R is your correlation coefficient. Okay? Oh, wow, that's a really big R. R is your correlation coefficient. It can go from -1 to +1. Okay, and there's a scale there. And that can also be 0. Okay, when you're at +1 or -1, you have basically a perfect model of your data. Okay, the closer that you get to an R value of 0, the less good. That's not proper English. The closer your R value gets to 0, the worse your model is, basically. Okay, so you can see that right here in the middle. Do you see this? Like, there's a bunch of random data, and when they're trying to model it, the computer, whatever, they came up with a circle. So there's no great model for these data points. Like, if I try to draw a line this way, that's supposed to be a line. If I try to draw a line this way, I'm not really getting a great model. If I draw it this way, I can't really, any way I draw this, I'm not really getting a great model of it. So this is an example of an R value of 0 because I really don't have that great of a correlation. So basically, these guys are the best, B-E-S-T, best, right? And right in the middle is the worst. So you're not aiming for an R value of 0. You either want it to be 1 or -1, okay? And then you'll see here in my bottom graph that we started off with that these R values are about 0.6. So they're kind of like middle of the road, right? They're not perfect models, but they're not awful models, right? They kind of get it, but they're not going to be perfect. Okay, does that kind of make sense what that is? Now, the reason that we have a +1 and a -1 R value is that because we call things that are positive over here, we call these a positive correlation. Okay, because when one thing increases, the other increases, right? It's like a direct variation. When I sell more hours, when I spend more hours selling my Girl Scout cookies, I increase the amount that I sold. Those are a positive correlation. And that's when we have a +1. We're aiming for a +1 R correlation. Okay. Over here, right? Over here, anybody have a guess what these are? These are a negative correlation. Now, a negative correlation doesn't necessarily mean a bad thing. It's not necessarily bad to have a negative correlation. It just means that your data is, negatively correlated. So, in this case, the number of hours I spend selling, the less Girl Scout cookies I sell. Obviously, that's not a good model for that, right? It would be something else like, here, right from your book. There's a graph with a negative correlation of number of people that have a number of subscribers. Oh, cell phone versus corded phones. So sales of cell phones versus corded phones. So as the years have gone on, the sales of home phones have gone down. That would be a negative correlation, right? So having a negative correlation doesn't mean it's bad, because you can still, if you get to a correlation of -1, you've kind of made that perfect negative correlation. Okay, so does that make sense, kind of what we're trying to do? We're kind of modeling the data. We're trying to get a R value, which R stands for the correlation coefficient. We're trying to get an R value of as close to 1 or -1 as possible, because that's what's going to basically fit our data in the best way. Okay. What's one other thing, just to kind of wrap this all up together, what's one other thing that we know about from our friend Slope Dude? What do we know about slope when we have a line like this or this? What kind of slope do we have? Do we have positive or negative? We have a slope that is increasing from left to right, right? That would be a puff positive slope. So that makes sense that our R value would be positive, right? And then over here on the right-hand side, we're going nice negative, right? We're going down the hill, nice negative. Yep, positive. There you go. Nice negative down the hill, right? So we have a negative correlation. So it's nice that it all kind of wraps together like that. Right? Okay, so then in terms of what you're doing for your homework, I have look at problem number 4 and number 8 in your book. So I'm going to do something kind of risky here. I don't have my book that I can obviously pull up. We don't have it there. Let me, be risky and search Google live. Never know what you're going to get, especially if you can't talk. Da, da, da. Here we go. We can use some of these. Okay. I don't know, I like that one. This'll work. We'll do this. Okay, so, make this picture bigger. So this is kind of like the examples from your book. It's actually not that hard to do when you click on a link. Here we go. All right, so if I look, and I know it has the label above it, but if I look at this initial graph right here, right, would we say that these data points seem to have a strong correlation? So would you think that well, first of all, and I know again it's listed at the top, I should go like this so we don't have to look at those words. There. All right, so this one that's hidden, I know you guys already totally saw it, but that's okay. If you just had to tell me, was this a positive correlation, a negative correlation, or no correlation, what do you think? This upper left-hand graph. Does this have a positive correlation, a negative correlation, or no correlation?
Positive.
Yeah, it's got a positive correlation, right? Because it's increasing over time, and it looks like the data is kind of graphed together. Okay? So we have a positive correlation. If you had to guess, well, since it's a positive correlation, we know it's going to be some number between 0 and 1, right? So do you think that, would you call this correlation value of R, would you call it 0, 0.5, or 1? Which one do you think that would be closest to? And this is just kind of a gut check. Like, what do you think? Well, it's definitely not 0 because 0 means it's scattered all over the place, right? I would say this has actually a pretty strong correlation. So if I had to say which number it was closer to, 0.5 or 1, I would say it's actually closer to 1 because this has a pretty strong correlation. Okay, that's as opposed to this graph over here. This also has a positive correlation. If I was trying to draw the line through here, I would make it positive, right? But it's not all that great at modeling my data if I tried to draw a line through there. So I would say, I know what I need to do. I would say that the second graph probably has an R value of around 0.5, or maybe even a little less, 0.4. Right? So this, when I try to draw my line of best fit, look at that, my data is pretty close. Right? Here, when I try to draw my line of best fit, it's definitely a positive number, but it's not that perfect, right? So this one, if I had to guess, it's definitely not 1, but the R value between 0.5 and 1, it's closest to 1. Okay. Over here, if I had to distinguish between 0, 0.5, and 1, I would say this one has an R value of about 0.5. Okay. It's not perfect. It's not awful. It's kind of, right? Again, these have the pictures on them. So let's look at this guy down here on the bottom right. If I go draw this, okay, this is a negative correlation, right? It's decreasing. It's nice negative, right? It has a pretty strong correlation. So I would say that if I had to estimate, this is closest to an R value of -1, right? Because it's pretty close. And then I know you guys can see no correlation here, but this last one, there's no great way to draw a line. I really can't tell you what it is. So something like this would have an R value of 0, right? It just has no correlation. Kind of all over the place. All right, everybody feel good about that? Pretty exciting. It's actually really cool. So then if you go to a tool like Desmos, you can actually calculate those R values. So let's do a quick activity. I'm trying to think, how many of us are on the call? There's 5 of us. There's enough of us to make some data here. Okay, so let's see. Let's make, this is Desmos. You can do this also in your TI calculator, so I'm happy to show you how to do that. What we're going to do is we're going to make a table. Nope, that's not what I'm trying to do. Done. We're going to make a table. Why is it not letting me make a table? Oh, I need to add a table. There we go. All right, so we're going to make a table of, I was going to do number of pets in our family, but that's not going to be helpful. My brain isn't working at the moment. All right, let me come back to that. Let's do this problem, and then we'll come back to that. I will come up with a good example from our class here in a minute. But my brain is not working at the moment. Let me see here. So I think I'm going to do number 27 from your book. We can kind of come back to this data, but I'm going to do number 27 because I think it's a little bit more interesting. If you don't have your book, it's okay. I'm going to read it to you. I'm on page 119. Okay, so in your book, it says, there's a table, and it says, the table shows the numbers of countries that participated in the Winter Olympics from 1980 to 2002. And it says, make a list, use the table to make a list of data pairs where X represents the years and Y represents the number of countries. So we can do something like this in a graphing tool by making a table. So how I make a table in Desmos is I go here and I say add a table. Okay. If you have a TI calculator, does anybody on here have a TI that they're also using? All right. Well, if you do, having a moment here, I did this so many times. If you do, you can actually go under graph and table, and there's a table feature underneath there as well. Okay. So, Aaliyah, let me tell you how you do that. So, Aaliyah, if you're making your table on your calculator, you want to hit the stat button, which is like top middle-ish. Stat. And then you want to go under to edit. And there's the thing that says list 1 and list 2. So you can make this under list 1 and list 2. And if I can't quite explain it over the online, I can show you in class too. Okay. So in Desmos, we're going to make a chart. So in 1980, there was 37 countries. And you guys, if anybody has their book, make sure I type in right. 1984, we had 49 countries. 1988, we have 57 countries. 1992, we have 64 countries. 1994, 67. 1998, 72. And 2002, we have 77. Does anybody know the Olympics are every 4 years? Why do we have data from 1992 to 1994? This is an off-topic math question. So the Winter Olympics, yeah, the Winter Olympics, right? The Winter Olympics are still also every 4 years. But and they were at before 1992, from 1992 and before, they were the same year as the Summer Olympics. So like there was a Summer Olympics in 1980 and a Winter Olympics in 1980. And there was a summer in 1984 and winter in 1984. And then they decided that it was easier logistically and obviously for television viewing, that if they staggered the Olympics so that the Summer Olympics happened, and then 2 years later the Winter Olympics happened, and then 2 years later the Summer Olympics happened. So in 1992, the next year should have been 1996, but they went ahead and held a Winter Olympics 2 years later so that they could start staggering the Winter and Summer Olympics 2 years apart versus having them on the same cycle every 4 years. So, all right, side note about Olympics. I do love the Olympics. All right, so if you wanted to make a list of your X and Y's, this is how you would change a table of data into a list of X and Y. Okay, now if we wanted to draw a scatter plot of this data, we would need to, wow, that looks crazy. If you were doing this manually, right, you have your data, you're going to draw an X and a Y axis, right? So down here at the bottom, we would put year, right? We would put year. And over here on the side, we would put number of countries. My pen doesn't want to work today on the screen. Countries. Okay. And then we could graph the data, right? In 1980, we had 37 countries. And obviously, we would make our scale a little bit better. In 1984, we had 49 countries and so on. So you can manually plot your data, right? You can also use a tool to plot your data. Well, I did put this in Desmos, but you're like, I don't see it. The problem is that our X values are in the 1900s and we're going from 0 to 10. So we either need, one option is to zoom way out, right? You can do that. Oh, there's my data over there. All right. Or you can change your table or your data range to reflect what's in your table. So how you do that on Desmos is you go into your settings, and you can see here the x-axis right now is shown from negative 1400 to positive 3200. Well, I only have my data from 1980 to 2002. So really, if I go from 1975 to 2005, and you can see that now I have a much better view of the X values of my data. The Y values of my data are not so good, so I need to fix that up, right? Again, go in here. It looks like my Y values range anywhere from 37 to 77. So I'm going to go ahead and just start my graph at 0, not 11, at 0. And I'm going to go up to about, we'll go up to like 100. Okay, so now you can see by putting in your, putting in a better domain and range, putting in a better view of your X and your Y, then voila, we have a nice graph of our data. Okay, and Desmos is even fancy. You can even label your axis. So you could put your X-axis as year and your Y-axis as number of countries. You want to get super fancy. Okay, and we can kind of close this up and we got a nice graph. So this is a plot of our data. Okay. So now looking at this data, does this data of the years and the number of countries participating in the Winter Olympics, does this have a positive or a negative correlation? Positive. I agree with you. I agree with you, Otto. It has a positive correlation, right? It looks like if I drew a line through it, it would go up this way. Do you think it has a strong correlation, like close to 1? Do you think it's closer to 0.5 or do you think it's closer to 0? Closer to 1. I agree with you, Otto. Closer to 1. Okay, so now I want to talk about how do you actually draw a line of best fit? Yay. How do we actually draw this line that fits best? One option is just to randomly draw the line, right? That's kind of an option. How do we actually figure out what this line of best fit is? Do you think you could do it without using any tools? So one thing that you can do is you can kind of try to draw a line that looks like it goes through most of the data, right? My line's not perfect, but that kind of looks like it goes through most of my data, right? Everybody okay with that? Now, it looks like my line goes through, oh, I don't want it to be, I want to just make it a little bigger. Sorry. Technology challenged here today. Okay, so it looks like it goes through about this first data point down here and maybe this data point up here. Okay. This data point down here, remember, was in 1980. We have 37 countries participating. And up here we have in 1998, right? We had 72 countries participate. Okay, if I wanted to write an equation for this red line, could I do it? Do you think you could do it? You have 2 points on a line, right? Could you write an equation that maps this out? Yeah, we could, right? We just talked about on Monday that any line always has this one equation. Y equals m, oops, my m's really big, mx plus b, right? How do I figure out the slope when I have 2 points? The slope is my change in y over my change in x. So I could do 72, right, minus 37. That's my change in y over my change in x, which is 1998 minus 1980. So if I do this calculation, I've got 72 minus 37, that's 35. 1998 minus 1980 over 18. So I have 35 over 18. So I get a slope of about, it's 1.94. So I get a slope of about 2 for my best fit line. Okay. If I really wanted to be approximate, I'll just go with 2. Y equals 2x plus b. Yep. Oh, there you go. Auto, thanks. 35 over 18, right? So that's cool. Now, how do I figure out where my y-intercept is? Where do I figure out where my y-intercept is? Well, I can't just extend my line forever to figure that out, right? But I do have 2 sets of data, and if I put one of those 2 in, I can figure out what my y-intercept is. So when x is 1980, right? Y equals 37 plus b. So if I solve for b, I get 37 minus 2 times 1980. I'm doing like a little bit of fast math here. B equals negative 3,923. So I plug that back in. My line of best fit is y equals 2x minus 3,923. Okay. Everybody okay with how I kind of came up with that? We're going to use our skills from how do we model lines to actually model real data. Now, if I go back to Desmos and I plug in this line that I think fits best, let's see if we did a good job. Okay, so I have my line. I also have y equals 2x minus 3,923. And that's the line that we just came up with. Look at that. It actually models our data pretty well, right? We have a pretty good model. I would say that our R value is probably 0.9, at least on this. So then if I asked you, and I know this doesn't actually work for, well, it could work. If I asked you to predict how many countries participate in 2006, could we do that based off our data? We could, right? We can go up here to 2006 and say that based off of our previous data, we would estimate that about 89 countries would participate. Right? Or I could say, oh, well, in 1976, how many countries participated? Well, based off of the data, in 1976, we had 29 countries participate. Okay. The model works best, though, in the in-between. Now, it doesn't really work for this because we're talking Winter Olympics. We know it's every 4 years. But if this was some other data, the model is going to work best in between. Because is this true? Like, if I zoom out to 2018, almost there. 2018, do you think 113 countries participate? We can't necessarily say that, right? Because we don't, as time goes on, there's only a limited number of countries in the world. The model, we can't extend the model out that far. Really, the model is best in this area here. Does that make sense? Is this cool? I think it's cool. I think it's pretty cool. All right, I just looked it up. I Googled it. There were 92 nations in 2018. So the model kind of falls apart, right? Kind of like flattened out about here, but up to there. One last thing I want to show you on Desmos, and this also you can do on your TI. So when you actually want to use your calculator, okay, when you actually want to use your calculator to make a line of best fit, and we're going to do this later, but I just want to show you because I think it makes sense in this section. There's a special way you write it. It's a little bit weird. So if you see up here, my table is X sub 1 and Y sub 1. If I want Desmos to come up with the perfect model for this, I have to write X sub 1. Nope, backspace. Approximately equals M X sub 1. And I'm not expecting you to know this. I just want to show you this while we're here. Plus B. So here's my Y equals MX plus B. Okay. You'll see that Desmos actually uses the data and they make a regression. So their line that they made, their best fit line is in green here. So it's pretty close to our blue line, right? So when they are trying to make a Y equals MX plus B that is the closest to our data, and they do that, the regression is a whole set of calculations where they look at every point and which one is closest. They come up with a slope of 1.768. So pretty close to our slope of 2, right? And a y-intercept of negative 3,460, which is, not far off from our rough estimate. And their R value that they can come up with for their line of best fit is an R value of 9.9854. So they can model this data pretty well. And I think we did a pretty good job of modeling it too, right? We did a pretty good job modeling our data. It might not have a R value of 0.985, but it has a pretty good R value. So I just wanted to show you that that Desmos and actually your TI calculator does regression. This is called regression. And that's when you have a set of data and you actually model it. So like I said, this is one of my favorite things to do because it's like, oh, I can actually use data. Like I can use data that, I've gathered from a study, and I can make a model for that data and use that model to share with other people. So I know it's kind of geeky. I think it's kind of cool. Hopefully it makes sense. Your homework shouldn't be that difficult. I think in your homework, they're going to give you much easier numbers than this. But you should be able to, when you have a set of data, be able to graph it and then be able to make a line that goes through your data. Okay, and then use that to predict from there. So try out 2.6. Keep working on that homework. We will definitely wrap up chapter 2 next week. It might be Monday that we wrap it up, but Monday or Wednesday. But we have 2 sections left in chapter 2. We have absolute value functions, and we have linear inequalities, graphing those. So thanks, guys. I know that was a lot we got through today, but hopefully that was somewhat interesting. I think it's kind of cool. And please send me a message if you ever have any questions, all right? Bye, guys.
Bye.
Bye. Thanks for coming.